Okay, welcome back. And now we're going to start Unit 2 or Chapter 2. And we're going to start with Section A. And this is all about to understand, solve, and explain problems. This is about problem solving. So let's get started. Okay, so to understand how to solve problems, we're going to go through a three-step process here. And it's basically like I just said, understand, solve, and explain. Okay, so step one is understand the problem. Okay, think about the problem, what it asks you to do. What are you trying to find? What's the goal of the problem? Okay, draw a picture or a diagram if it makes sense to do that. Sometimes you can't draw a picture, but a lot of times you can. And the old adage that a picture is worth 1,000 words is absolutely true, because if you can draw a picture, you can understand what they're doing from the picture. So a lot of times I will always encourage my students to draw a picture. Ask yourself what the solution should look like, right? So based on what they're asking you to do, you should have an idea of what the solution should look like, and then that'll help guide you. Try to map out a path either mentally or on paper. Typically, paper works very well for a lot of people. Okay, in fact, in a lot of cases, it's better because to keep track of your thoughts and what you're trying to write down. And so, try to map a path that will lead you from your understanding of the problem to its solution. And then continually revisit your understanding of the problem, because again, you may not understand it fully, and then as you get into it, you may want to change certain things because your understanding becomes better. Two, solve the problem. So once you figure out what what they want you to do, and you have a path of how to get there, then you just basically use whatever techniques that you come up with to do that. So obtain the needed information from the data, or the data, right? So when you read the problem, the first thing I always do is write down the information that they give you, and write down what it is that you're looking for, or if there's data, write down the data, or make sure you make note of the data. Okay. And then for multi-step problems, be sure to keep an organized, neatly written record of your work. You've got to have good penmanship. You've got to be able to read your own writing, and you've got to be able to do your work in an orderly fashion, especially if you're going to be studying for an exam, right? You want to be able to go back and re-look at the problem, and you want to understand what you wrote down, right? That also basically, as an aside, if you have good penmanship and you work at doing things in a nice organized manner, then you'll do that on the exams, which will help you get more points from the person grading the exam. Now, if it's an online exam, obviously there's not a lot to be graded, but still you want to have a notebook for the obvious. If something does happen, you'll have your work handy that you can submit. Double check at each step of your work to avoid carrying any errors through, like compounding errors, to the end of your solution. Okay. Constantly reevaluate your plan as you work. And then three, the final step is explain your result. Be sure that the result makes sense, right? So the one question you will always want to ask yourself whenever you get an answer is, look at it, does it make sense? Do the units make sense? Okay. That's going to be a key indicator, because if your answer doesn't make sense, then maybe you made a mistake somewhere. Recheck your calculations once more, or even better, find an independent way to check your results. Or hey, have somebody else look at your results. See if they come up with the same solution, or see if they find a mistake. Identify and understand any potential sources of uncertainty in your result. If you made any assumptions, ask yourself, were those assumptions reasonable? Okay. And then write your solutions clearly and concisely, using complete sentences to make sure that the context and meaning are clear, right? So especially in word problems, you always want to make sure that your answer is written in a way that answers the question, okay? In the context of the question. Okay, now units. The units of a quantity describe the quantity, measures, or counts, right? So those are the units of the solution, right? So we always want to pay attention to the units. Unit analysis is the process of working with the units to solve problems. So that goes back to what I just said a moment ago, is making sure that you ask yourself, hey, do the units make sense? Or better yet, as we talk about unit analysis, ask yourself, hey, what units should my answer be in based on what they want me to do and what I'm given? What should I, based on the units given in the problem, the different values that I'm given and their corresponding units, and what they want me to find as the goal or the answer to the problem, what should I expect my answer units to be? Okay, so here's an example. Okay, you're buying 30 acres of farmland at $12,000 per acre. What is the total cost of the farmland? Well, think about this. Okay, so we've got 30 acres, right? That's the total area of farmland. And we're being told that it's $12,000 per acre, right? So per, right, means division, right? It's $12,000 per acre, right? So how is that going to translate? So it's $12,000 dollars over acres. We're told that we're buying 30 acres of land, and we want to know what is it that they want us to find? Total cost. So what would we think that the units should be for the total cost, right? It's cost. Well, if it's $12,000 per acre, then we would imagine that the total cost is going to be in dollars. Okay, so we would expect our answer to be in dollars. Okay, so let's go through this. Understand the question. It talks about cost, and one of the given units is dollars, so we expect the answer to be in dollars, just what I said. Now, once we know what to do, we solve the problem, right? So how do we solve the problem? Well, we know that our answer has to be in dollars. And like I said, they gave us one piece of information as the cost per acre, which was $12,000 per acre, and per means division. So notice how we have dollars over acre. And then we also are given the total number of acres, okay? So if we know that our answer should be in dollars, well, notice that the acres should cancel. We should not have acres anywhere in our answer. So notice how the acres is on top, because if we put this in a fraction, it's basically the same as 30 acres over 1, right? And so notice the acres on top cancels with the acres on the bottom. And so what happens? We end up multiplying across the top, and we get what? $360,000, because the unit that's left on top is dollars. And then of course we found the purchasing that, what does this tell us? It means that in order to purchase 30 acres of farmland, we are going to have to pay $360,000 for all 30 acres. Okay, now show operations in units clearly to answer the question, what is the total distance traveled when you run 7 laps around a 400-meter track? Okay, so here's a couple of things. Well, we need to know what a lap is, right? A lap is one distance around the track, right? So what do we know? Well, we know that one lap then is what? Well, we're told that the track is a 400-meter track, which means one lap equals 400 meters, right? So we can write that down, right? One lap equals 400 meters, right? And so we want to know what the total distance is. So there you go. That's what they want us to find, the total distance. So the goal is to find total distance. So what should our final answer be in? Well, it's got to be a measurement of distance. And what measurement of distance are they giving us? They're giving us meters. Okay? So we know the total distance has to be in meters. Okay? So again, how do we get meters? Well, we got to set it up using what we know from the problem. Now that we understand what they want us to do and what they're giving us, now we got to calculate it. Okay? So we could express the same idea as 7 laps of a 400 meter. Therefore, the problem requires multiplying 7 laps by 400 meters if you run meters you run per lap, right? So that's what we got up here. So 1 lap equals 400 meters, which means what? We can write this as 1 lap per, oops, not lap, 1 lap per 400 meters, or we could say that 400 meters, it's 400 meters per lap, right? Either way is okay. It just depends on the problem and how we're going to write it. We could write it either way, okay? So notice how that we did. So they used this one because why? Well, because we know our final answer has to be meters. So we need to have meters on top. And so we've got 7 laps, right? That's the total number of laps that we have to run. And so it's 400 meters per lap. So notice that if we write this over 1, the laps on top will cancel with the laps on bottom. Think about it as canceling numbers, right? If you have the same units on top of a fraction and you're multiplying by another fraction as the units of laps or the same units on the bottom, then those laps are going to cancel each other out, okay? And so notice how the only units we're left with is meters, which is what we want. And so all you do is multiply across the top and the bottom, and you get 2,800 meters. And so the total distance you would run if you went 7 laps is 2,800 meters. And that makes sense, right? So again, ask yourself, does that answer make sense? Yes, it does. Okay, everything makes sense with that answer. Okay, now here are the key words that you want to use, okay, that you want to pay attention to. So per, like I said before, per is an indicator of division, okay? Again, miles per hour, miles per gallon. What else? There's all kinds of ones. Oh, I can't think of it off the top of my head. But anyway, there's lots of examples of where per comes in. Okay, so of is typically used for multiplication. So if you say 30% of $600, right? That of means you're going to multiply those two things together. If I say I want 3/5 of the amount of flour that's needed, right? So the word of is going to indicate multiplication. Also, the hyphen will indicate multiplication. So this comes in a lot of cases, like when you're dealing with physics, or if you've taken chemistry or physics. So sometimes these units come up with hyphenated words, like kilowatt hour, this measurement of energy, okay? Or you could do foot pounds, right? Foot pounds is another one, or Newton meters. Newton meters is another one that has a hyphen in it. So anytime you have a hyphen or the word of in a math problem, it's going to indicate multiplication. Square, so that's raised to the second power. So anytime you see the squared, square feet or feet squared, those are indicating powers, right? So in this case, area, right? So and by the way, always one good way to remember or to read this is think about feet squared as feet times feet. That's going to help us with our unit analysis when we look at canceling units, like I was just talking about. And then of course cubes, right? Cube or cubic, that's also a power, and that's raised to the third power. So again, these are the way we usually will see it. Now, typically we always see the units as feet squared or feet cubed, right? As in volume, right? So area versus volume. So we would say this is cubic feet or feet cubed, or cubic inches, cubic centimeters. It's the same thing. Okay, so now conversion factors. A conversion factor is a statement of equality. Statement of equality that is used to convert between units. Okay, so you may have seen, you saw this in the earlier slide. Okay, so when we use conversion factors, this is what we're talking about. It's a statement of equality. So 12 inches equals 1 foot is a conversion factor, and we can write it as a fraction, right? Because what we're saying is 12 inches is the same as 1 foot. So this is the same as 1. That, you know, basically not the number 1, but it equals 1 in the sense that they're the same. Okay, like again, 24 hours is equal to day, so you can write it this way, or like I said, you can flip it and it's the same thing. Okay, so these are called unit factors. Okay. Okay, conversion factors. Now let's look at this. Convert a distance of 9 feet into inches. Okay, so we're starting with 9 feet. So I'm going to start with 9 feet up here. Okay, and we want to get to inches. So the goal is we want to write an equivalence of going from feet to inches. So what is the equivalent? What is equivalent to 9 feet in inches, right? So we start with 9 feet and we need to get over and we need to convert to inches. So we need a conversion factor that relates inches to feet, right? And we know what that is, right? We know that 12 inches is equal to 1 foot, and we need to multiply by some factor, right? That's going to give us what? Feet over here, because that's the goal. We need to get, or I'm sorry, not feet. We start with feet. We need inches. Okay? So how are we going to get there? Well, we're going to use this. So remember what I said. We want, whatever we have start with, feet is on top. We want to have feet on the bottom to cancel because we need inches on top, because that's what our final answer needs to be. So whatever our final units need to be, that needs to end up on top of the fraction on the last factor. Okay, since this is the last factor here. So what are we going to do? We're going to write 12 inches over 1 foot. And so the feet will cancel. And guess what? Now we left with inches. That's the only unit left. Now we multiply across the top and divide by the bottom, right? Multiply across the top and the bottom, which we just get 1 here. So we can ignore that because it's just 1. And then 9 times 12 is 108. Okay, so we find out what? That 9 feet is equivalent to 108 inches. Okay. Come on now. All right, so here's a funny comic for you. You feel like Foxtrot? So again, you can convert using the same thing. So 94 days, right? So how does that work? Well, you have 94 days, right? You're starting with 94 days and you want to end up with seconds, right? So how did she do that? Well, she starts with 94 days. You find out there's 24 hours in a day, right? So there's one conversion factor, right? Because sometimes you can't go directly to seconds. You know, very few people I would think would know that there's 8,121,600 seconds in 94 days, right? So we wouldn't do it that way. We would start with what we know. So here's one conversion factor. Well, we know there's 24 hours in 1 day. So we use that conversion factor. And then we say, okay, well, how do we get from hours? How do we convert hours? Well, then we're going to do what? We're going to use the fact that there's 60 minutes in 1 hour, right? See, now we've got days on top, day on the bottom, hour on top, hour on the bottom. Now we want to go from minutes to seconds, right? We know that there are 60 seconds in 1 minute. And now we've got minutes on the bottom and top. And so now what happens here? Well, now we can cancel out the units that are on the top and the bottom. And then we're all only left with seconds. And then all we do again is multiply across the top and multiply across the bottom, which just gives us 1, and we get our final answer. And that's it. All right, now what about powers? Okay, here's where we have to remember, how do we write the cubic or units that are powers, right? We write them out, okay? We write them out as multiplication, like we do here, okay? And so again, a square yard, remember, a square yard is a measurement of area. So if you look, we've got 3 feet on this side and 3 feet on this side. So this is 1 yard by 1 yard, or it's 3 feet on this side and 3 feet on this side. So in order, we just use the fact that we can rewrite this as yards times yards, which is feet times 3 feet. Each yard is equal to 3 feet, and you get 9 square yards. So you could use this, or you could remember that 1 square yard, 1 square yard is equal to 9 square feet, okay? All right, so it says, how many cubic yards of soil are needed to fill a planter that is 20 feet long, 3 feet wide, and 4 feet tall? Okay, well, a couple of things here. Well, we want to know cubic yards, right? So that's the goal. We need cubic yards, but they give us the dimensions of the planter in feet. And we're talking about volume here. So what do we need to do? Well, we need to first find the volume that they have in feet. That's the way I would do it. So we're going to do 20 feet times 3 feet times 4 feet, right? And so, which again, I'm going to write this out long ways, but this is what? It's 20 times 3 times 4, and then we've got what? Feet times feet times feet, right? And so what does this become? Well, 20 times 3 times 4 is 2,400, right? Oh, nope. 240. Okay, and so now this becomes feet cubed, or cubic feet. So 240 cubic feet. Okay, so that's the volume of the planter. So now let's start with our 240 cubic feet over 1. And now we've got to convert it to cubic yards. Well, now, so the way I'm going to do it is I'm just going to use what I know. So I'm going to know that I need feet on the bottom because I got feet on top, so I need to cancel with feet on the bottom. And so I know that 1 yard is equal to 3 feet, but that only takes care of one of the feet, right? So if I cancel this, I still got feet squared. Well, let's do it again. 1 yard over 3 feet, okay? And that's going to cancel with another one. And then finally, 1 yard over 3 feet, okay? Okay. And then, of course, this is going to equal 240 over, not 9, 27, and it's yard, and it's cubic yards. And then, so of course, we can use a calculator to figure this out, which gives us what? Which gives us 80 over 9, which is going to give us an approximation. So we get approximately 8.9 cubic yards of soil. So the answer is okay, how many cubic yards of soil are needed to fill the planter? We're going to need approximately 8.9 cubic yards of soil. So if I was going to order this for a real planter, I'd just say give me 9 cubic yards of soil. Okay. But again, the answer is if they wanted you to round to the nearest decimal, it'd be 8.9 cubic yards. All right, now let's look at the Kentucky Derby horse race. Is 10 furlongs. How many miles is the race? Okay, so we need to know what a furlong is, and we need to know the conversion from between furlongs and miles, right? So that'll have to be given to us. So again, in the textbook, they give us that 1 furlong is 1/8 of a mile. And so we're going to use that information. So this is the same as 0.125 miles, or 1/8 of a mile, or 0.125 mile. Okay, and so we can use this to convert. Okay, so how do we do that? Well, we start with 10 furlongs. Okay, and it's what? We need furlongs on the bottom to cancel the furlongs on top. So this is going to be what? 0.125 mile over 1 furlong. And so again, multiply across the top and the bottom. That'll give us 1.25 miles. So the Kentucky Derby is 1.25 miles. Look at that. Okay, so now the metric system. So there are 2 systems that we use. One system that we use is the international metric system. It was invented in France in the late 18th century. Okay, so that'd be the late 1700s. For 2 primary reasons. One, to replace the many customary units with just a few basic units, and 2, to simplify conversions through the use of decimals that had a base 10 system. Okay, makes it much easier to convert between units, different types of units. Now the basic units of length, mass, time, and volume for the metric system are the meter, kilogram, second, and liter. So for length or distance would be the meter. For mass would be kilogram, which is denoted by kg. Meter is just a lowercase m. You've seen that before. Second is for unit of time. And then the liter is a capital L for volume. Now, here are the prefixes that you're going to want to familiarize yourself with. So for small values, right, we use these prefixes. So these prefixes are used to denote small values. For large values, we use these prefixes. Okay? Now, incidentally, these prefixes come from the Latin. And these prefixes come from the Greek translations, okay? Or the other way around. Do I have that wrong? No, I think that's right. Yeah, I think I might have these switched, but I'm pretty sure it's centi. Yeah. Yep. I'm pretty sure that's right. Okay, now let's convert 2,759 centimeters to meters, right? So the key here is the prefix here. right? So the unit is meters, right? Centi, right? Centimeters are smaller than meters. So the centi is telling us how many centimeters are in a meter, right? So let's go back to the tables again. So notice here are the abbreviations for the different. So these are the abbreviations we would use, okay? Now, but remember, so notice how the value here is divided by a power of 10. So for small numbers, you're dividing by powers of 10. For the large numbers, you're multiplying by powers of 10. Okay, so centi basically is saying 1/100th of whatever the unit is. Deci means 1/10. Milli means 1/1000th, and so on. Whereas deca means 10, hecto means 100, kilo means 1,000, right? So let's go back. So now, what we're saying is that this is a 100, right? So that's saying that 100, so a centimeter is 1/100th of a meter. So in other words, there are 100 centimeters in 1 meter. So if we want to convert from centimeters to meters, we're going to use that fact. So 2759 centimeters over 1. And we're going to use the fact that there are 100 centimeters in each meter. And so I put centimeters on the bottom because we need to cancel with the centimeters on the top. And of course, the answer needs to be meters, which perfectly works fine because we've got our final unit is in meters. So that is correct. And so all we have to do is multiply across the top and the bottom. Oops. And we get this, which just turns out to be this. And guess what? All we had to do was move the decimal point over 2 spots, because remember, this is the same as 2759 over 10 squared. So we're dividing by 10 twice. And remember, every time you divide by a power of 10, you're moving the decimal point. So remember, there's an imaginary decimal point at the end for all whole numbers. You're going to move the decimal point to the left, right? So in this case here, you're going to move the decimal point to the left 2 spots, which gives you the answer. If you multiply by a power of 10, then you're moving the decimal to the right, however many times that the exponent is. But we'll do an example of that. All right, so the marathon running race is about 26.2 miles, and we want to convert that to kilometers. They want to know how far is it in kilometers. So we want the answer in kilometers. So we've got, so again, we start with 26.2 miles. And now we've got to have a conversion for kilometers to miles, right? Or miles to kilometers, right? So again, this is something that you can get on a table, or if you know what the answer is. So in this case here in the table, it shows that 1 mile is equal to 1.6093 kilometers. Okay? Okay, so what we'll do is we will then multiply by a conversion factor, or a unit factor. And so what do we need? We need miles on top. Okay? And we know that 1 kilometer is equal to 1.6093 miles. So the miles cancel, and we end up with 26.2 miles. Well, 26.2 divided by 1.609, right? And so that's going to give us an approximation of 42.2 kilometers. All right, now let's look at temperature units. We're going to talk about three temperature units. We'll start with Fahrenheit and Celsius. Fahrenheit is part of the English or the SI system. Okay, Fahrenheit is a part of the English system. It's used in the United States. It defines that the freezing point of water is at 32 degrees Fahrenheit and the boiling point of water as 212 degrees Fahrenheit. Of course, this is based on standard atmospheric pressure and temperature, which is I believe it's 1 Pascal and 25 degrees at sea level. Okay, and then of course the rest of the world, which this is part of the metric system, uses Celsius, which is 0 degrees Celsius is freezing point of water, and 100 degrees Celsius is boiling point. So notice it's base 10. Okay. And then of course the other unit that we're going to talk about is Kelvin. The Kelvin scale which is the same as the Celsius scale, except for its 0 point, which corresponds to negative 73.15 degrees Celsius. Okay, so that would be, we don't have that degree sign. A temperature of 0 Kelvin, right? So 0 Kelvin corresponds to this negative 273.15 degrees Celsius. It's called absolute zero. It's a theoretical temperature by which atoms stop moving. Okay, we've never reached it. We've gotten really close, but we haven't reached it. And again, it's the coldest possible temperature. Now, we don't use the degree sign with Kelvin. Okay, we just use the capital K. So here's the three scales side by side. Okay, so notice that 212 degrees Fahrenheit is the same as 100 degrees Celsius or 373.15 Kelvin. Okay, and then 32 degrees Fahrenheit is the same as 0 degrees Celsius, which is equal to 273.15 Kelvin. Okay, and then 0 Kelvin is the same as negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. All right, so now here are the formulas for converting between the different temperature scales. Now, I would recommend not using the 1.8, okay, because it's an approximation. Okay. So, and plus it's a decimal. The fraction actually I think works better, but you know. So here's the thing: if you memorize one of these, you can get the other one easily by solving. So here, if you have this formula here for converting from Celsius to Fahrenheit, right? And so 9/5, so it'd be what? F equals 9/5 C plus 32. Then you can easily get this Celsius formula by just solving for C in the top formula. Just solve for C and you'll get the second formula. So you really only have to memorize the first formula. And then of course, since Kelvin and Celsius are related, really, once you convert to Celsius, then converting between Celsius and Kelvin becomes just an addition or subtraction problem, because you're either just going to be adding 273 degrees to go from degrees Celsius to Kelvin, or you're going to subtract 273.15 degrees to go from Kelvin to Celsius. Okay, come on. Come on now. There we go. Okay, so the average human body temperature is 98.6 degrees Fahrenheit. What is it in Celsius and Kelvin? So we're gonna convert to Celsius first. Okay, we're using one of the formulas. Okay, so we're gonna convert from Fahrenheit to Celsius, right? So again, if we remember, Fahrenheit is equal to 9/5 9/5 9/5 C plus 32. That's right. Okay. So now all we have to do is, because we want to convert to Celsius, then we want to use what? We're going to use what? We're going to subtract 32 from both sides, so it's going to be what? And then we're going to multiply by the reciprocal of the 9/5. So C is going to become what? It's going to become 5/9 times the quantity F minus 32. And so we can use this formula and just plug in for Fahrenheit. And then once we get to Celsius, then we can just use the 273.15 degrees and subtract. Okay, so again, they use the 1.8, but again, you're just going to subtract and then multiply by 5/9, and so we get 37.0 degrees Celsius. Okay, so that's, and then of course, all we have to do is add 273.15 degrees to get this Celsius temperature. Okay, so because remember, 0 degrees Celsius right? Is equal to, oops, 1.5 Kelvin. All right, so the total temperature in Kelvin would just be 310.15 Kelvin. All right, so now here's another example. It says, at a French department store, the price of a pair of jeans is 45 euros. What is the price in US dollars? And then we're going to use the exchange table, the exchange rates on the table 2.4 in the textbook. So again, we're just going to use those conversion factors like we have. So on the table, it says 1 euro is $1.32, so $1.32. And so we're going to use that conversion factor, and we're going to use it as a fraction. So we're either going to use this one or this one, right, depending on what we're solving. So in this case here, we're starting with 45 euros. So we need to have the conversion factor with the euros on the bottom to cancel the euros on the top that we start with. And so this is the one we're going to use. And so we take 45 euros and we multiply by this conversion factor. The euros cancel and we end up with approximately $59.4. So $59.40 for the cost of the pair of jeans that we were out in Europe. So here's the exchange table for different exchanges for different currencies. Okay, so now here's another example. Let's say we're in Canada, and Canada sells gasoline for Canadian dollars. That's what this stands for, Canadian dollars. It's 1.34 Canadian dollars per liter, right? Okay. Now we're going to use again the currency exchange rate on table 2.4, right? So Canadian dollars right? So depending on what we're doing, so it's either going to be, this is dollars per foreign, so, or foreign per dollars, right? So we're going to use the 1.005 to convert to dollars. Okay? Oops. Yep, there it is. And then also, because we want to go from we want to convert into dollars per gallon, we're also going to have to convert between liters and gallons. So we're going to do two conversions here. So we're going to go from Canadian dollars per liter to dollars per gallon. Okay, and notice we start with 1.34 CAD over liters, and we convert first to dollars, right? So the Canadian dollars cancel, and now we've got dollars on top, so we can stop there. And now we want to convert the liters to gallons, so we use this conversion factor, and so liters cancels with liters, and we end up with gallons on the bottom. So what do we can stop because we've got dollars over gallons, and we can multiply across the top and multiply across the bottom, and we get approximately $5.10 per gallon is what the cost is, the equivalent cost. All right, and that's it. So that takes care of section A for chapter 2, and we'll come back and we'll do section B next time. Take care, guys.